Assalamualaikum. Today's topic under chapter 5, continuity and Bernoulli's equation. And previously I've already focused more on continuity equation and introduction. Now we're gonna learn about the Bernoulli's equation. So Bernoulli's equation is one of the most important or useful equations in fluid mechanics. It may be written, this is general equation for Bernoulli's equation. We have 2 points, 1 and 2, and then we write Bernoulli equation on the point 1 and point 2. So P1 over rho 1g plus U1 square over 2g plus Z1 equal to P2 over rho 2g plus U2 squared over 2g plus Z2. This Bernoulli's equation has some restrictions in its applicability. So we are focusing more on these types of Bernoulli's equation. So to use this Bernoulli's equation, there are some restrictions. So the number one, flow is steady. So to use this Bernoulli equation, the flow must be steady. Okay, in and out is equal. Mass in equal to mass out. So there will be no accumulation in the system. Okay. Number two, density is constant. And to use this equation, you must apply to incompressible flow. For the compressible flow, there will be a little bit different because, as we know, compressible flow have different velocity when been compressed, and that's why this Bernoulli's equation is only applicable for incompressible flow. Number three, friction losses are negligible. As I mentioned before, this Bernoulli's equation is general Bernoulli's equation. There will be some extension to this Bernoulli's equation where we have to add here with friction head, and then here we have another one which is HP, represent pumping head. So to use general Bernoulli's equation without HF and HP, this Bernoulli's equation restriction is up to friction losses are negligible. So if we move to chapter 8, and if you learn in Bernoulli's equation, or you do some Bernoulli's equation problems in chapter 8, you might see this plus HF. Okay, and chapter 9 you will see another extension to the Bernoulli's equation where we include pumping head in our Bernoulli's equation. Last, the equation relates the state at 2 points along a streamline, a single streamline. This means that if you have a streamline and you want to develop, or you want to do a Bernoulli's equation at point 1 and point 2, you must apply Bernoulli's equation on a single streamline. You cannot do this. Okay, you have two streamline. Maybe this is pipe A and this is pipe B. And you are required to find what is the velocity at point 2A. For example, this is 2A, 1A, 1B, and 2B. Okay, you are required to find what is the velocity at point 2. And you know that when the flows occurs, or you want to apply to the flow, you want to find what is the velocity of fluid at point 2b, you must apply Bernoulli's equation. And maybe you have two streamlines, and then informations you want to do a Bernoulli's equation and you just take 1a and 1b. That is totally wrong because you are applying Bernoulli's equation at two different streamlines. And in order for you to apply Bernoulli's equation, it must be in the same streamline or in a single streamline. You can apply Bernoulli's equation point 1 and point 2a, 1a and 2a, or 1b and 2b. So if you are applying Bernoulli's equation for pipe A, your Bernoulli's equation will become P1A, okay, P1A over rho 1A G plus U1A square over 2G plus Z1A equal to P2A over rho 2A G plus U2A square over 2G plus Z2A. And when you are applying Bernoulli's equation at pipe B, so you must change the subscript into 1B and 2A to 2B. Okay? Remember, to apply Bernoulli's equation, you must apply it on the same streamline. Do not cross the streamline. If you have two pipes, you want to find what is the velocity at point 2B, and you suddenly apply the Bernoulli's equation between point 1A and point 2B, it is totally wrong. Okay? Apply Bernoulli's equation only on a single streamline. Do not cross. Okay, that is the restrictions of Bernoulli's equation for this form. Okay. Next. So in Bernoulli's equation, there are three elements that has been considered to derive the Bernoulli's equation. As you can see here, we have three different, change the color first. There are three different terms here. First one, it is the first term, second term, and third term. So those three terms are actually represent energy for the system. Okay, for example, if you want to throw a ball from at elevations of maybe h, so you throw a ball to the ground, and if at this point you might have potential energy, high in potential energy and low in kinetic energy. As the ball falls and reach at the bottom of at the ground, and at this point pressure energy will be decreased and kinetic energy will be increased. So it same goes with Bernoulli's equation, but Bernoulli's equation will have to add another terms, what we call as pressure energy. So the first term is pressure energy. P1 over rho 1G is a pressure energy. Second term, U1 square over 2G is a kinetic energy. Third term is potential energy. Okay, so we have potential energy. Equation is mgz, and then we have potential energy per unit weight, and we have z. Okay, so the potential energy equation is mgz, but if we want to change the potential energy to potential energy per unit weight, the equation is only z. Okay, kinetic energy half mu squared. If you want to do kinetic energy per unit weight, it will be u squared over 2g. So at any cross section, we can refer to this figure. The pressure generates a force. The fluid will flow moving the cross section. So works will be done. If the pressure at cross section AB is P and the area of the cross section is A, then the force that applied on AB is equal to PA. Okay, when we derive and we get that the term pressure energy is equivalent to rho over rho g, or in other words, work done per unit weight. So we have three different types of energy being considered in the Bernoulli's equation. First is pressure energy, second is potential energy, and third is kinetic energy. So by summing all these energy terms, we will get this general equation. Okay, P over rho g plus u square over 2g plus z equal to h. Okay, total energy per unit weight. So this is only one point. If you are applying up to 2 point of energy, 2 point, and you want to find the total energy, that would be P1 and P2. Okay, so as all of these elements of the equation have units of length, they are often referred to as the following. So from this equation, we call the first term is pressure head. Why head? Because the unit is in meter. So all this unit is in meter. So you will have unit of meter. So that's why pressure head means that the pressure in unit meter. Velocity head, velocity in unit meter. Potential head, potential in unit meter. So this velocity head is actually kinetics head. Okay, so the equation here is in unit of meter. Okay, we have potential head, kinetic head, and potential head. Pressure head, kinetic head, and potential head. So let's take a look at this. Okay, I change the color of this pen first to blue to make it easier for you to differentiate between the slide notes and my writing. By the principle of conservation of energy, the total of energy in the system does not change. Okay, thus the total heat does not change. So the Bernoulli's equation can be written. So from previous Bernoulli's equation here, this equation and total energy in the system does not change. Therefore, P over rho g plus u squared over 2g plus z is constant. So the Bernoulli's equation applies to condition along a streamline. We can apply it between 2 points, 1 and 2, on the streamline. 2 points joined by a streamline. Let's take a look at this figure. So we have point 1 and point 2. Okay. For example, let's take a look. Okay. If we want to apply the Bernoulli's equation at both points in this system or the flow, so we can use total energy per unit weight at 1 equal to total energy per unit weight at 2. So we have total energy per unit weight is H. Previous equation, we have H. H is represent total energy per unit weight at point 1. Okay, we have here total energy per unit weight at 1. So we have H, capital H1 equal to capital H2. which means at point 1 total energy at point 1 and total energy at point 2. Now we know that this H is equivalent to this P over rho G plus U2 over 2G plus Z. So we just apply this, substitute this equation into this. But you must remember, for the pressure, there will be a subscript here. So you have to put P1. Subscript 1 represent section 1. So over rho 1, density at point 1, G plus U1 square, velocity at 1 square over 2G plus Z at 1 equal to P2. We go to the point 2. Okay, we have to substitute the value of pressure at point 2 over rho 2 G, velocity at 2 G plus, density 2 G plus velocity at 2 square over 2G plus Z2. So from here, we know that this is the total energy at point 1 is equivalent to total energy at point 2, because conservation of conservation of energy said that the total energy in the system does not change. Whatever energy value here would be equal to energy value at point 2. So energy value at point 1 is equivalent to energy value at point 2. Remember, this is steady flow. There will be no accumulation in the system. So total energy per unit weight at 1 equal to total energy per unit weight at 2. So we can express Bernoulli's equation not only in terms of heat, we can express it in terms of pressure and energy. So from here, we know that this energy is in terms of heat, which is meter. So if we want to convert into pressure energy, we just have to multiply all those terms by rho G. So here, if we multiply by rho G, we will get the pressure term. Okay, all these units will be in Newton per meter square. Okay, you have to multiply all of these units. Rho over rho G times with rho G, you will get P over rho G times with rho G, you will get P. U squared over 2G times with rho G, you will get U2 squared over 2 times with rho. And then Z times with rho G, you will get Z rho G. And if you want to convert into pressure energy, in terms of energy, from this equation, you must multiply it with G. So P over rho G times with G, you will get P over rho, plus U2 squared over 2G times with G, you will get U squared over 2, and then the last term is Z times with G, you will get ZG. Okay? Normally, in fluid mechanics, in this subject, we will use heat in terms of heat, Bernoulli's equation in terms of heat. So therefore, this equation normally used for our calculation that involve Bernoulli's equation. Okay, the terms is in heat. Okay, let's take a look at the application of Bernoulli's equation. See this figure, a contracting expanding pipe. We have section 1 and section 2. So when the Bernoulli's equation is combined with the continuity equation, the two can be used to find velocity and pressure at point in the flow connected by streamline. Normally, we are using Bernoulli's equation. At some points, we cannot solve Bernoulli's equation. Why? Because we have so many unknown. In order for you to solve that unknown or to reduce the unknown, Maybe the unknown comes from velocity. So in order for us to reduce the unknown, we can use continuity equation to help Bernoulli's equation. And the continuity equation will reduce velocity terms from two unknown into one unknown. As we know that this continuity equation is u1a1 equal to u2a2. So we have, for example, in the flow of the fluid, in the pipes, we have velocity 1 and velocity 2. But the velocity is not been given for both points, and then we have to reduce this equation, and the Bernoulli's equation is used in that equation question in order for us to determine what is the velocity, either at point 1 or point 2. And then we cannot solve the Bernoulli's equation. Let's take a look at this. If we want to find what is the velocity at point 2 or point 1, we must have, if we apply this Bernoulli's equation, and we cannot solve because there would be two unknown in the system. The fluid velocity at point 1 and point 2 are not given in the question. So how to solve? Other information such as like P1 and P2, Z1 and Z2 will be given, but normally velocity will not be given in the question. Therefore, you have to find a way to solve. And in order for you to reduce the number of unknown, now you have unknown U1 and unknown U2. So in order for you to reduce into one unknown, because if you have two unknown, you cannot solve this Bernoulli's equation. You must reduce it into one unknown. How to use it? How to reduce it? By using continuity equation. That's why I show you here. From continuity equation, we have u1a1 equal to u2a2. So let's say we want to take u1 out from the equation, and we left the Bernoulli's equation with u2 terms. So u1 equal to u2a2 over a1. So after you rearrange the continuity equation, then you substitute the u1 equation into this equation. So you will left this Bernoulli's equation with only one unknown, which is u2. Okay, rearrange the equation, then you will get what is the value of u2. Okay, now let's take a look at this question. A fluid of constant density 960 kilogram per meter cubic is flowing steadily through the above tube. Not above, actually, below. This below tube. The diameter at section D1 is 100 mm and D2 is 80 mm. The gauge pressure at 1 is 200 kilonewton per meter square, and the velocity is 5 meter per second. So we have here velocity is 5 meter per second. And then we have density 960 kilogram per meter cubic. And then diameter is 100 mm. And diameter 2 is 80 mm. Now velocity is 5. Pressure at 1 is 200 kilonewton per meter square. So you have to convert this into this. We have kilonewton per meter square. To substitute this value into the Bernoulli's equation, you must remove kilo and turn it into 200 times 10 to the power of 3 Newton per meter square. Okay, kilo is times 10 to the power of 3. So what is the gauge pressure at section 2? So we have to find what is the pressure here. Okay. So this is incompressible flow. Therefore, rho at 1 is equivalent to rho at 2, which is 960 kilogram per meter cubic. Now, there is a flow of fluid inside of this system, inside of this contracting, expanding pipe. Therefore, you have to apply Bernoulli's equation because there is a change of energy from point 1 to point 2. Okay? You must not use the equation in chapter pressure and head in order for you to determine what is the pressure at point 2. Okay? Chapter 2, pressure and head is only applicable for the velocity at rest. For the fluid at rest. Okay? For the fluid flows in a pipe and there is a change of energy, so you must use Bernoulli's equation in order for you to solve, either to find what is the pressure at any point or velocity at any point. Okay, you must aware of this application. Okay, do not apply chapter 2 equation in flow of the fluid. Okay, it will be totally wrong. Now we will apply point 1 and point 2 Bernoulli's equation. So we will get, so pressure P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2. So we have point 1 and point 2. Total of energy at point 1 is equivalent to total of energy at point 2. Now, we're focusing more on the question. We have to find what is the pressure at 2. Okay? But before that, we have to look at one by one terms. Now, take a look at the pressure energy at point 1 and point 2. Of course, pressure is already been given. Yes, this info cannot be removed. So we want to remove any terms that can be removed from this system. So we have to see the pressure energy. So P1 over rho G, yes, we do have pressure energy, and that is what we need to calculate, pressure at point 2. Then we go to the velocity U1 and U2. Okay, if the area at point 1 and point 2 is the same, therefore you can exclude or you can remove U terms. Okay, now if area 1 is equal to area 2. So we have this area point 1 and area at point 2 is the same. Therefore, at this point, the velocity will be the same. And then you can cancel out U1 and U2 term. If A1 is not the same as A2, so let's say you have this contracting pipe. So this is your point 1. So the area here is not the same as area at here, point 2. 1 and 2. So the fluid will flows here. So the area 1 is not the same as area 2. Therefore, U1 U1 is not equal to U2. Then your Bernoulli's equation will left with terms U1 and U2. You cannot cancel it out. Okay, now we take a look at this condition. Our condition here is A1 is not equal to A2. As we can see here, the diameter at 1 is 100 millimeter and diameter at 2 is 800 millimeter. 80 millimeter. Therefore, we cannot use the first condition A1 equal to A2. So we have area 1 is not equal to area 2. Therefore, U1 is not equal to U2. You cannot cancel out. When U1 and U2 is the same, you bring this U2 to the left hand side, then it will cancel out because it has the same value, velocity value. Okay. Now we take a look at the last term here is potential heat. So if you want to apply Bernoulli's equation here, so for the pipe, you will take Z at the center of the pipe. Okay, at the center of the pipe. Sorry, my line is not straight. So this is the point 1 and this is point number 2. So point number 1 is Z1, point number 2 is Z2. If you have that term from here, so this is your datum, your Z1, let's say you have Y, and your Z2 is the same as Z1 position. Therefore, this is Z, this would be Y. So if you take a look at this equation, Z1 and Z2, if you bring this Z2 to the left hand side, it will be Z1, it will become Z1 minus Z2. If Z1 and Z2 is equal number of equal, which means the value is the same, therefore you will cancel out this term Z1 and Z2. So for a horizontal pipe, such as this case, it will have the same point. Therefore, Z1 is equal to Z2. Then we can cancel out Z1 and Z2 term. And it will be left, your Bernoulli's equation, left with the terms of P1 over rho G, U1 squared over 2G, equal to P2 over rho G plus U2 squared over 2G. Rearrange this equation because we want to find what is P2. So the equation will become like this. Okay, P2 equal to P1 plus rho over 2 U1 square minus U2 square. So you may test and try to rearrange this equation. Okay, now in this question, we already been given with U1 velocity. But what about U2? If we do not have U2 and we do not have P2 value, this equation will have two unknown. Wait, in order for you to solve this, we know that we have continuity equation. Therefore, the continuity equation will remove one of these unknown and remain one unknown for your Bernoulli's equation. You have two unknown P2 and U2. By using continuity equation, you will remove another one unknown and you will left one unknown, which is P2. Okay? By using the Bernoulli's continuity equation, A1 U1 equal to A2 U2. So you rearrange equation because you want to change, substitute the value of U2. Value of U1 is already been given. Therefore, you need to change U2. you don't want this value, you don't want these terms, and you want to substitute a value or u1 terms in your equation. Okay, for example, you want to change it and you want to make it only u1 terms, therefore you have to change u2 terms. Okay, now we have, in this question, we have u1, therefore we have to change this u2. So rearrange this equation, u2 is equal to a1 u1 over a2. So we get d1 over d2 square u1. So you substitute the value of diameter here for diameter 1 and diameter 2 and square times with the velocity at 1. So you will get this velocity. Okay, 7.8125 meter per second. So now we can calculate the pressure at section 2, because as you can see here, we already solved the unknown for the unknown u2. Okay, now we left with one unknown. u1 is already been given, rho density also been given here, pressure also been given. So all the information has been completed. Therefore, you substitute all the values inside this equation, and then you will get what is the value of P2. So you have to remember, in this question, the pressure is 200 kilonewton per meter square. So you have to change kilo to 10 times 10 to the power of 3. So which means 200 kilonewton per meter square, meter square. So you have to change into 200 times 10 to the power of 3 Newton per meter square. Okay, so you will get your value of P2 is around 882.7 kilonewton per meter square. Okay, so flow through sharp edge orifice. If we have a tank and then there will be a sharp edge orifice over here, so if we enlarge point here, we will get this kinds of figure. Okay, the shape of the hole edges as they are sharp to minimize frictional losses. So we can see here there is a sharp edge, and this is to minimize frictional losses. Okay, and the only contact is at the very edge. So looking at the streamlines, you can see how they contract after the orifice to a minimum value when they all become parallel. At this point, the velocity and pressure are uniform across the jet. This convergence is called vena contracta. Okay, from the Latin contracted vein. It is necessary to know the amount of contraction to allow us to calculate the flow. Okay, we can predict the velocity at the point at the orifice using the Bernoulli's equation. So the vena contracta is this. This is vena contracta. So you know that when we have a sharp edge orifice, we have two different areas. So we have this, change color. Blue. So we have this area, okay. So cross-sectional area, for example, and then we have another area here where the flow will move through it. So this is A actual, the actual area where the fluid will pass through, and not at this area. So normally we will give you at this area the diameter of this area, but we do not give you the A actual. But we can actually solve that issue in order for us to get what is the actual. So this is what we call this point. The AC here is what we call as AC theoretical, and A actual is A actual. Okay, in order for you to determine what is the A actual, you have to calculate from A theoretical, then you have to multiply with some constant, and then you will get what is the A actual. Now we have to apply Bernoulli's equation from now we need to find what is the velocity at point 2. Okay, normally in the question will not give you the points where you have to locate or you have to apply your Bernoulli's equation. It is up to you where you want to apply your Bernoulli's equation and how to find and how to choose your point is based on pressure, energy, pressure, velocity, and Z. Okay, if you have pressure, now take a look at this. Here, let's say I want one here and or one here. Okay, for example, you want to take another point. You don't want point 1 to be here. You want 1.1 to be here. Okay, to make it easier, I will put it 1A and 1B. For example, you want to apply Bernoulli's equation at point 1A and 2. So let's take a look at one by one. First, at point 1B, what about the pressure at A? Do we have pressure here? So if you have the height and you can calculate the pressure of point 1A, then you can solve it. And another thing, second is you have to take a look at velocity. Do we have velocity at point 1A? No. And the another term is Z. If you been given with the height of with height from bottom to the point of 1A, then you should have no problems for you to solve Bernoulli's equation from point 1A and 2. But now we have Z, let's see. And pressure, we do not have pressure at here. If in the question give you the point, the pressure at point 1A, then you can solve, then you can apply at this point. You may tick right here. Okay, take a look at those three terms. Now we have pressure. Velocity, we do not have velocity. Z, yes, we have Z. Can we solve this equation? Okay, normally pressure will not be given here. We cannot find values of pressure here. So if you can find it, then you may tick this. And then from these 3 points, you do not have the values of velocity. And if you want to apply the continuity equation, what is the diameter? So it relates to the diameter. Do we have the diameter of the tank? Of course, no. Sometimes it will not give you the diameter of the tanks. Therefore, you cannot choose. And you cannot solve for the velocity. Why? Because if you, yes, I know, if you want to apply the Bernoulli's equation, and then you have two terms, you have two unknown. Okay, U1 and U2. You may solve this equation by applying continuity equation. But wait, in the continuity equation, we have U1A1 equal to U2A2. So what is the area area 1? So you cannot solve it. So U1 will remain unknown. Therefore, you cannot choose point 1A. Okay? Point 1A cannot be used. Let's take a look at point 1B. So what about pressure? Yes, because this is open to atmosphere. Therefore, point here is equivalent to atmospheric pressure. What about the velocity? So because of tank, this is tank, compared with the diameter of the orifice. So U tank, area tank is much bigger than area orifice. If this area of the tank is too big for the compared to area of orifice, therefore velocity at orifice will be much more small or lower than the volume decrease. So which means the velocity here, we have the velocity of air reduced every time. So velocity at this point would be less. So velocity at tank 0.1 B. So when this is happening, so you may assume that U tank at 0.1 B is approaching to 0. So this area is too small compared to area of the tank, and then the level of this flow will reduce and reduce a little bit, and velocity here will approaching to 0, maybe 0.01 meter per second, because this area is too big. Then the velocity at 0.1 B is equivalent to 0 meter per second. What about Z? Yes, Z is already been given in this question. So here we can see that we have pressure, we have velocity, and we have elevation. Therefore, we can use 0.1 B for U, 1 B and 0.2 to find what is the velocity at 0.2. Therefore, you apply Bernoulli's equation at 0.1 B and 0.2. So if we apply the Bernoulli's equation, then we will get, okay, P1 B rho 1 B G plus U1 B square over 2G plus Z1B equal to P2 over rho 2G plus U2 square over 2G plus Z2. So we take a look at one by one terms in this equation. So let's take a look at the pressure energy. So we have pressure at 1B and pressure at 2. So pressure at 1B is atmospheric pressure. Therefore, we can neglect this. Okay? Since we are dealing with pressure head, therefore, we are not considering atmospheric pressure in our calculation. That's why we are zeroing the terms, the pressure energy terms. So now take a look at the pressure 2. So this fluid will flow out, and at this point, it will flow out to the atmosphere. And then at point 2, the pressure is P atm. So P2 is P atm. Therefore, we can exclude this P2, zeroing it. Then we take a look at velocity 1B and velocity 2. So yes, previously I've already told you that we have velocity at 2, but we do not have velocity at 1B, since velocity at 1B is approaching to 0, or it is below than 0, then we are zeroing velocity at point 1b. Therefore, here we will be 0. Then we have leave the terms with z1b u2 squared over 2g plus z2. So rearrange this equation, we will get this. So where does this h comes from? So we rearrange the equation, okay, z1 minus z2. So u2 square is equal to 2g, z1 minus z2. So let's take a look at the term z1 and z2. So if z1 is 0.1b lah, okay, z1b, and we have z2. So let's say I want z2 as my datum. If z2 is my datum, therefore I will zeroing the point 2. And point 1 z1b is equivalent to, we have here is h. So we have h. But here we need to take a look at the point. So this is z1b and we have z2 here. So if z1b is above z2, then you have to substitute a positive value into z2. So now we have positive value, right? So positive h. So we just replace it with h. Let's say if you want to choose z1b as your datum, so I will zeroing the point at z1b. So you have z1b and then point 2 is z2. So if point 2 is below than z, therefore you will substitute negative value to z2. Therefore your z2 is negative h. So this method applicable for all the points and all the elevation in the Bernoulli's equation, not necessary to z1b and z2. If you have 2 points, then you select one of those points as your datums and take a look at the another point. Then you have to substitute. If that point is above, the second point is above your datum, then you have to substitute positive value. So if your second point is below than your datum point, this is based on your selection, z1b and z2, below than your selection, your datum selection, therefore you have to substitute z2 with negative value because it is below than your datum. Okay, so now you have z1 minus z2. So let's say I take z2 as datum, therefore my z1 is h minus 0. So I will get h here. So let's say this is option number 1. Let's say I took option number 2. I take now option number 2 where z1b is my datum. So I will put 0 minus, my z2 is negative h. So you have to replace here with negative h. Therefore, your z1b minus z2 is h. So both of these will be the same. Okay, remember positive and negative value. So let's take a look at here. That's why we have h here, because z1 minus z2 is h. So rearrange and then you will get u2 equal to z2g h. So that is your velocity. But in the for this velocity, it is a calculated value, or It is a theoretical value. If you want to do something, if you want to calculate what is the velocity by using the equation, that is your theoretical velocity, because you calculated based on the data, okay, given to you. Then you will get the values of u. Okay, that is theoretical velocity. But in the sharp edge orifice, we know that there will be a little bit different, because there will be a different area here. So we have A actual and area theoretical. So the flows will flow on this area. Therefore, we have to multiply with some constant or correction factors in order for us to correct the values of this theoretical velocity, to correct this theoretical velocity. So at this point, to correct to find what is the actual velocity, so this is u actual theoretical. So to find u actual, you have to multiply with coefficients of velocity. So your u theoretical here from this calculated value must be multiplied with coefficients of velocity, and you will get u actual. So this CV, coefficients of velocity, normally been given. It is depends on the manufacturer. They will give you this coefficient. So sometimes this coefficient is in the range of 0.97 to 0.99. So same goes to area. We know that previously A actual, the diameter for this sharp edge orifice is at this point. So we will be given this point to this point. So we have this diameter, okay, theoretical. And then to get the actual value, the actual area, you have to multiply with coefficients of contraction. Therefore, A actual equal to coefficient of contraction times with A theoretical. Okay, A theoretical is pi d squared over 4. Okay, so the discharge through the orifice is given by, we know that the equation for discharge is Q equal to AU. So if you are using this equation, you will get Q theoretical. And in order for you to get what is the Q actual, you have to substitute this A actual and U actual. So we substitute, we will get CC times with A orifice, and then CV times with U orifice. So this equation is actually, so A actual is CC times with A theoretical, or A orifice is A theoretical. Then another term is CV times with U theoretical. So this equation is then rearranged, CC times CV, A orifice, and U theoretical. So from here, we can simplify CC and CV terms. So we introduce a new coefficient CD, where this CD is equivalent to CC times with CV. Okay, this is coefficient of discharge. So this coefficient will be given in your question. So coefficient of discharge is times with the A orifice, U theoretical. So your Q actual will become CD times with A theoretical and U theoretical. Okay, that is the equation to solve what is the actual value of actual discharge of your system, for sharp edge orifice, this system lah. Okay, it will be applicable to any of the equipments. Okay, not necessarily to sharp edge orifice. Okay, the question might ask you maybe for the flow in the pipes, or maybe the flow in any types of equipments, because all the equipments will have its own coefficient of discharge, because that coefficient of discharge is based on the frictional losses that will be experienced by those equipments. In order for you to get what is the actual value, then you have to multiply with that coefficient to get what is the actual value. Okay, that's all for the Bernoulli's equation. Thank you.